Hello everyone. Today we will solve problem number 2. We will analyze this statically determinate frame. Uh, Means we have to find AFD, SFD and BMD for each member. For each member we have to draw axial force diagram, shear force diagram and bending moment diagram. So if you recall from the previous video, I have mentioned the steps. What are the different steps that we need to follow in order to analyze statically determinate frame? The very first step we have is a reaction offered by the support. So here at point A you have hinge support, at point D you have roller support. So we know from the basic, hinge support is offering two reactions, one is vertical and another one is horizontal. So we are naming it as VA, and here VA means vertical reaction at A, HA horizontal reaction at A. And at roller support we have only one reaction perpendicular to the support or vertical reaction VD. So we need to find this. So to find VA, I will take moment about point D. Moment about point D equal to 0. Means I have to follow a direction A to D. Means left to right. Okay, I have to follow this direction. So here I have assumed the vertical reaction upward for A. I am taking moment about point D, and which is equal to 0 because it is a roller support. So we know at roller support the moment is 0. Okay, so we have to take all the forces into consideration in order to find moment about point D. So here VA into 5. This is VA. VA is acting upward, and here the perpendicular distance with respect to point D is 5 meter, and it is creating clockwise moment. Then we have this HA. This line of action of the HA is here. Okay, and the perpendicular, this is 5 meter, this is 3 meter, this will be 2 meter. Okay, and this is creating clockwise moment. This is creating clockwise moment. So we know from the sign convention that when we are following a direction from left to right, the clockwise moment will be positive and anti-clockwise moment will be negative. HA into 2 meter. Okay, now we have this point load here. The line of action of the point load is like this. This is 2 meter, this is 3 meter, this has to be 1 meter. Okay, and again this is creating clockwise moment. It will rotate this joint in a clockwise fashion. Plus 10 into 2. Then you have this point load. This is a point load. Line of action of the point load is like this 20 kilonewton, 3 meter from point D, plus again this is creating clockwise moment, 20 into 3. Then you have this UDL. Total load of the UDL is concentrated at the center. Total load of the UDL is 15 into 5. This is the line of action of the total load of the UDL, and the perpendicular distance from D is 2.5 meter. This is 2.5 meter, and this is creating anti-clockwise moment. This total load of the UDL is creating anti-clockwise moment. Minus 15 into 5 into 2.5 equal to 0. Okay, so by solving this equation, VA, you will get VA equal to 11.5 kilonewton First we need to find this HA. How to find this HA? How to find this HA? You have to use summation of f of x equal to 0. F of x equal to 0. All the forces along the horizontal direction is equal to 0. Minus HA because it is pointing towards left side, plus 10 plus 20 equal to 0. So HA you are getting here, HA equal to 30 kilonewton. 30 kilonewton. So you have to substitute this HA value here and solve for VA. V you will get 11.5 kilonewton. Now we need to find VD. We have done with the calculation of HA, VA, we have to find VD. So for VD we have to use summation of f of y equal to 0. Summation of f of y equal to 0. All the forces in vertical direction is equated to 0. Plus VA minus this total UDL is going downward, VA is going upward, that is why we have taken positive. UDL is going downward, so we have to take it negative. Total load of the UDL is 15 into 5. Then VD is going upward, plus VD equal to 0. We know the value of VA. Substitute the value of VA here. You will get VD equal to 63.5 kilonewton. So this is how we have to calculate the reactions. We have to calculate the reactions. Now we have to go for the calculation of axial force, shear force and bending moment. Now we have to go to step number 2. Step number 2, we have to analyze the members separately. Analysis of the member separately, or else we have to isolate the member, and then we need to find axial force, shear force, bending moment separately. So here if you see, the very first member is AB. Draw the free body diagram of member AB and then find axial force, shear force and bending moment and then draw it. So first we will just draw the free body diagram of member AB. In free body diagram you have to show the loads acting on member AB and then the different forces acting on member AB. So we have this A, B. We know the reaction at A. VA is 11.5 acting towards upward kilonewton. We have HA pointing towards left direction, so HA is equal to 30 kilonewton. You also have loads. You also have load on member AB, 10 kilonewton. Okay, this is 3 meter and this is 2 meter. Now we have to talk about balancing of member AB. We know the reaction at A. We need to find reaction at B. We know vertical reaction at A. We know horizontal reaction at A. We have to find reaction at B. Okay. So now see here, 20 kilonewton is also there. We have to take that. In order to balance this member AB with respect to vertical direction, 11.5 kilonewton is going upward. Here the vertical reaction will be downward, 11.5 kilonewton, because it has to be balanced with respect to vertical direction. In order to balance with respect to horizontal direction, we have to find the reaction at B. So see here, 30 kilonewton is going towards left, 10 kilonewton is going towards right, 20 kilonewton is also going towards right. So this is balanced. 30 kilonewton is going towards left and as well as 30 kilonewton is going towards right. Okay, if you try to find the reaction here, assuming any direction, you will get 0. You can use this equation summation of f of x equal to 0 and go and try to find the reaction. Minus hb plus 20 plus 10 minus 30 equal to 0. So hb you will get equal to 0. Okay, now we can go for the drawing of axial force diagram. If you look at this here, the nature of the axial force is in compression and it is constant throughout the member. So here we can draw axial force diagram for member AB. It is compression in nature. So we know the sign convention for compression axial force. It is minus 11.5 kilonewton, 11.5 kilonewton AFD for member AB. Okay, now we have to quickly move towards the calculation of shear force. Okay, shear force. We know how to calculate shear force. You can see my previous videos. Again we will follow the same methodology what we have adopted in the previous video. Shear force at left of A, we have to look in this way. Okay, this is point A, this is point E, and this is B. At left of A, this is point A. At left of A, you do not have any perpendicular force to the member. Okay, so in this way we have to look. This is towards up and this is towards down. So we are following a direction A to B, means left to right. Whatever force is going upward, you have to take positive, and whichever force is going downward, we have to take negative. Okay, so in this way we need to calculate the shear force at various points. So at left of point A, shear force is 0. At right of A, at left of A is 0. You are going from left of A to right of A. One force is going upward, plus 30 kilonewton. Next point is E. Left of E, from right of A to left of E, you do not have any new force. You have to take same shear force. Okay, now right of E, from left of E to right of E, one force is going downward, so plus 30 minus 10 equal to 20 kilonewton. Okay, now next point is B, left of B, from right of E to left of B, you do not have any new force. Okay, the same shear force you need to write, 20 kilonewton. Then you have right of B equal to from left of B to right of B, 20 kilonewton is going downward. You can see here 20 minus 20 equal to 0. So now I can draw the shear force diagram. It will be like this. This is the datum for the shear force. Above datum indicating positive shear force, below datum indicating negative shear force. So left of A is 0, right of A is plus 30, left of E is 30 itself, right of E is 20. Okay, this is 30 kilonewton and this is 20 kilonewton. Left of B 20 and right of B 0 plus. So this is shear force diagram SFD for member AB. Now we have to go for the bending moment calculation. So we know bending moment at A. bending moment at A is equal to 0. Why it is equal to 0? Because it is hinge support. We know at hinge support bending moment is equal to 0. We have to calculate bending moment at E and bending moment at B because those are rigid joint. B is rigid joint, E is also rigid. We have to find. So bending moment at A is equal to 0. Bending moment at E, bending moment at E, we are following a direction A to E. Again A to E means left to right, clockwise moment will be positive, anti-clockwise moment will be negative. You can see here this will not come into picture because perpendicular distance is 0. 30 will come, 30 into 3 because you're calculating moment about point E, and this 30 will create clockwise moment. Okay, make this point fixed and apply force like this, and this will create clockwise moment. So 30 into 3. Okay, and no force, no other force than this. So your bending moment is 90 kilonewton meter. Then bending moment at B, from A to B, all the forces you have to consider. First is 30 perpendicular distance with respect to point B is 5 meter and it is creating clockwise moment. So 30 into 5. Then you have this 10 kilonewton perpendicular distance with respect to point B is 2 meter and this 10 kilonewton is creating anti-clockwise moment. So here minus 10 into 2. So the bending moment is 130 kilonewton meter. Now you need to draw the bending moment diagram. Datum, this is datum, above datum, below datum, above datum indicating positive bending moment, below datum indicating negative bending moment. Bending moment at A is equal to 0, bending moment at E is 30, this is 30, and bending moment at B is 130. So the variation of the bending moment is linear. Okay, because it's just a point load. There you do not have any UDL or UVL. You have the point load. For point load, the bending moment variation is linear. Linear means straight line. 30 kilonewton, 130 kilonewton meter. Kilonewton meter. A, E, B. Okay, this is about analysis of member AB. Now we have to go for the analysis of member BC. Okay, we have to go for the analysis of member BC. First draw the free body diagram of member BC. Show all the loads acting on member BC. We know from the problem that UDL is acting on member BC. BC is 5 meter in span. Now we have to make first the equilibrium of joint B. We know from the member AB we have reaction here. We have a vertical reaction which is downward 11.5 kilonewton. Horizontal reaction we have calculated which is 0. We have calculated this in the previous member. If you see, we have calculated the reaction at vertical reaction at B and horizontal reaction at B, which is equal to 0. Okay, the same thing you show here. Now we have to balance the joint B. This is joint B of member AB. This is joint B of member BC. So here at joint B of member AB, vertical reaction is downward. In order to have balance of joint B, here vertical reaction should be upward, 11.5 kilonewton. Horizontal reaction is towards left. This is not having any magnitude. To understand the concept of equilibrium, we are just showing the direction. So here it is towards leftward, here it should be towards rightward, 0 kilonewton. So we have balanced the joint B. Now we have to talk about balancing of member BC. Balancing of member BC with respect to vertical direction and horizontal direction. You have calculated reaction at B of member BC. You have to calculate reaction at C, vertical reaction and horizontal reaction. So horizontal reaction will be 0 kilonewton, because this is towards right. Here it should be towards left in order to have balance in horizontal direction. Now you see 11.5 is going upward. You take VC here, VC, and apply summation of f of y equal to 0 and calculate VC. In this way you can find VC, or else 11.5 is going upward and 15 into 5. 15 into 5 means 75 is going downward. 75, is it right? 70. Okay, 75 is going downward. So this is not balanced. You can use this equation. VC plus 11.5, both are going upward. This minus 15 into 5 equal to 0. Okay, so VC you will get, VC will be VC will be 63.5 kilonewton. You know what is the VC. You also know the bending moment at B. We have calculated bending moment at B. We got positive, means we have to take clockwise. So we have calculated bending moment at B. Here, what is bending moment at B? Bending moment at B is 130 kilonewton meter, positive. Show here clockwise, 130 kilonewton meter. Okay, now see here, axial force diagram is 0 because you have 0 kilonewton. AFD for member BC. Okay, what about the shear force? You have to calculate. Left of B 0, no force. Right of B, from left of B to the right of B, one force is going towards upward, 11.5 kilonewton. Next point is left of C, from right of B to left of C you are going, and the entire UDL is going downward. Okay, so 11.5 and the entire UDL is going downward. Take it minus 15 into 5, so you will get minus 63.5 kilonewton. Okay, now right of C, you are going from left of C to right of C, minus 63.5 from left of C to right of C. VC is going towards upward. What is VC? 63.5 plus 63.5. So shear force at C is 0. So draw shear force diagram. Draw shear force diagram to be like this. Okay, left of B 0, right of B 11.5 kilonewton. Okay, now left of C minus 63, right of C 0, plus minus 63.5 kilonewton. This point is called point of zero shear. We need to find this, because at point of zero shear you have maximum moment. We need to find that point of zero shear. Okay. Dear students, we need to find this point of zero shear. For that we have to use the concept of similar triangle. This length is 5 meter, the length of member BC. This point is point of zero shear. We don't know where is the point of zero shear. As of now we are denoting it as x, and we need to find x. For that we have to use the concept of similar triangle. Okay, so 11.5 divided by x, height of this triangle divided by base of this triangle, equal to height of this triangle 63.5, base of this triangle 5 minus x. So here you are getting x equal to, you will be getting 0.77 meter. Now we have one more point F. Okay, point F is at a distance 0.77 meter from B. We have calculated. Okay, now we have to go for the calculation of bending moment. So bending moment calculation, bending moment at B we have calculated 130 kilonewton meter. Bending moment at F, bending moment at F, you have to take all the forces into consideration, all the moments and the forces into consideration. Bending moment at F, you are traveling from B to F, you are following direction left to right, clockwise will be for positive, anti-clockwise will be negative. So here it will be like this. Bending moment at F is 130 kilonewton because you have moment at B, then this point load 11.5 into 0.77 because this perpendicular distance with respect to point F is 0.77 and it is creating clockwise moment. Then you have this UDL. The total load of the UDL will be concentrated at the center of this span. Okay, so it will be 15 into 0.77. Okay, and the perpendicular distance of this load with respect to point F is 0.77 by 2. So and this load is creating anti-clockwise moment. So it will be like this, minus 15 into 0.77, which is the total load. Okay, perpendicular distance with respect to point F is 0.77 by 2. So bending moment at F, you are getting 134.41 kilonewton meter. Okay, so bending moment at C will be 0. I will explain you how it is 0. I will explain you. We have to draw the bending moment diagram. Okay, this is datum. Bending moment at B is 130. Bending moment at F is 134 and here it is 0. The variation will be parabolic. This is 134.41 kilonewton meter. This is 130 kilonewton meter. B, F, C. Okay, so now we shall switch over to the analysis of last member, that is member CD. Last member CD. Draw the free body diagram of member CD. C, D, you do not have any load. The span of this, the length of CD member is 3 meter. You have one reaction here, VD equal to it is 63.5 kilonewton. Okay, and you do not have any load. So why I told you the bending moment at C is 0? See, if you want to calculate bending moment at C, you have to go from D to C, and you do not have any perpendicular force here or any perpendicular force on member CD. If you have any perpendicular load on member CD or perpendicular reaction, you will get moment at C, but you do not have any perpendicular loads. That means you will not get any moment at C. Okay, directly you can write bending moment at C is 0. Now we have again we have to use the same principle, balancing the member C, balancing this member CD with respect to vertical and horizontal. With respect to vertical, this is going upward, here it should be downward, 63.5. Okay, we don't have to talk about the equilibrium with respect to horizontal direction because there is no horizontal reaction here and you will not get any horizontal reaction here. Okay, so here it will be like this. Axial force diagram is compression in nature, 63.5 kilonewton, 63.5 kilonewton. Shear force is 0, SFD is 0, bending moment is also 0. What is bending moment at D? D is roller support. D is roller support, and at roller support bending moment is 0, and at C we know bending moment is 0. So you only have axial force diagram for member CD. Shear force is 0, even bending moment diagram is also 0. Thank you for watching my videos. Thank you.